Unit 4, pages 87 to 94, we're going to focus on molarity calculations. Solutions are different from solid samples in the respect that in order to deliver a certain quantity of solute, the volume and concentration of the solution must be known. The most common unit of concentration in chemistry is molarity, represented with a capital M. It's defined as molarity is equal to the moles of the solute divided by the total volume, or moles per liter. So, experimental preparation of a solution. You have your moles of solute over the total volume. So let's say the total volume here is 1 liter, and then you have your water in the solution, and then however many moles of solute you add, you would take that divided by the 1 liter, and that would give you the molarity of this solution. We usually make solutions in a volumetric flask. The solution is prepared by adding the desired number of moles of solute to a volumetric flask and then diluting with water until the total volume is exactly the desired quantity. Due to adhesive forces, the water is attracted to the walls of the glass, forming a negative meniscus, a downward curve, that can be very accurately aligned with a calibration mark on the container wall. That would be represented here in the diagram. So finding the concentration. Molarity calculations allow you to convert between volume and moles if you need to. Volume times molarity is going to be equal to moles, and moles divided by molarity is going to be equal to the volume. Exercise 4.29. If water is added to 15 grams of sodium chloride so that the total volume is 500 milliliters, then what is the concentration? These are our three equations. Molarity is equal to moles divided by liter, molarity times liters is equal to moles, and moles divided by molarity is equal to liters. It's very good to go ahead and start memorizing these three if you don't already have them. So because we want to know what is the concentration, then I want to use the equation set to solve for molarity because that's the unit of concentration. I'm going to need moles, so I have 15 grams of sodium chloride, and we're going to convert to moles. And remember that moles is equal to grams divided by molar mass, that little equation that we got in class. So we'll just take the grams divided by the molar mass, which is 58.44 grams per mole. And when we divide these out, we get 0.2567 moles of sodium chloride. We want to divide the moles by the volume in liters. We're given the volume in milliliters, and so we'll just convert that to liters by moving the decimal to the left 3 places. And now I'll just take this value divided by the 0.5, and that's going to give me my molarity, which is 0.513 molar sodium chloride solution. Example 4.30, if water is added to 7.5 grams of potassium sulfide so that the total volume is 250 milliliters, what is the concentration, or what is the molarity of, and this time we don't want to know the molarity of potassium sulfide, we want to know the molarity of the potassium ions and the sulfide ions. So first you need to draw out what's in the beaker. So here's our beaker, and we have our water. And when you place K2S into the water, you're going to get 2 potassium ions for every 1 sulfide ion. So the rule here is total moles divided by total volume is going to equal the molarity that you need. So first I need to get the molarity of the K2S. And we're going to do that the same way we did the last sample problem. Take 7.5 grams of potassium sulfide, convert that to moles by dividing by the molar mass, 110.27 grams per mole, and that's going to give me 0.068 moles of potassium sulfide. I'm going to divide this by the total volume, which is 0.250 liters, and that's going to give me 0.272 molar potassium sulfide. But I don't want to know potassium sulfide. I want to know the potassium ions, and I want to know the sulfide ions. So we need to break this down in an equation. Potassium sulfide is going to break apart into 2 potassium ions and 1 sulfide ion. So the equation would look like this. Potassium sulfide yields 2 potassium ions and 1 sulfide ion. And then you can put this molarity here, 0.272 molar, and now I can just use stoichiometry to figure out how much of each of these am I going to produce. So 0.272 molar potassium sulfide times, draw a line, And I'm going to bring down moles. We're doing a mole-to-mole ratio. Moles of potassium sulfide to moles of potassium ions. And so for every 1 mole of potassium sulfide, I'm going to produce 2 moles of potassium aqueous ions. And so we're going to multiply 0.272 times 2, and that's going to give us 0.544. That's going to be the molarity of the potassium ions, because notice here your moles cancel and these cancel, and you're left with molarity of potassium ions. And so we'll do something similar down here. Molarity of potassium sulfide times, draw a line, 1 mole of potassium sulfide produces 1 mole of sulfide ions, and therefore 0.272 times 1 is just 0.272 molar sulfide ion concentration. Again, these cancel, and I'm left with molarity of sulfide, which is what my unit is here. The conversion factor used to convert from liters to moles or vice versa is the molarity. Molarity times the volume is going to be equal to the moles, or moles divided by molarity is going to be equal to the volume. So exercise 4.31. How many moles of nitric acid are contained in 2 liters of a 0.2 molar nitric acid solution? So again, here are my 3 equations. Molarity is equal to moles divided by liters. Molarity times liters equals moles. Moles divided by molarity equal liter. Again, it's good to memorize them because it'll just be quicker in the long run. So the question is how many moles, which means I want to use this equation because it's set to solve for moles. It says moles equals. I want to take the molarity and I want to multiply it times the volume in liters. So my molarity is 0.200 molar times 2.00 liters, and that's going to give me 0.4 moles of nitric acid. So exercise 4.32, what volume, so we're looking for the liters, and that is going to be equal to moles divided by molarity. What volume of 0.3 molar nitric acid is needed to supply 2.0 moles of nitric acid? And so I'm going to solve for the volume, and I'm going to take 2.0 moles of nitric acid divided by its molarity, 0.3 molar, and that's going to give me 6.67 liters of nitric acid. Okay, dilutions are a really big deal. So here you have some water, and you're going to have a certain molarity of solute here. Like say we have our 4 solute particles here. So this has a high concentration because it has very little solvent compared to the solute. But then if you add more water, bring the water level up, you have diluted it. And so now it has a lower concentration or a smaller molarity. The basic idea of a dilution problem is that water is added to a solution and the volume changes, but the moles of the solute do not. Sometimes it's not always easy to figure out that an exercise is a dilution problem. You have to convert the words of the problem to a picture in your head describing what is really taking place in order to be able to understand that what is being described is a dilution problem. So I would say focus on any time there would be a volume change or if 2 volumes are added to one another. Exercise 4.33. How much 1 molar copper sulfate solution is required to make 250 milliliters of a 0.1 molar copper sulfate solution? And what you should notice is you have 2 different molarities of the same solution. So one of them is more concentrated and the other one is more diluted, which is how you know this is a dilution problem. And so they each must have 2 different volumes. So we can use our equation M1V1 equals M2V2. And because these are coupled together side by side, I'm going to make sure that they are a set in my equation. It doesn't matter if they are the 1s or the 2s, but I'm going to go ahead and make it the 2s. So I'm going to have 0.1 molar times the volume, 250 milliliters, and notice I'm keeping it in a unit of milliliter, equals, and on the other side, my M1 is 1.0 molar from here, and the question is, what is the volume? Note that I'm going to end up with my volume in milliliters since I left this volume in milliliters. And so to solve this, I'm going to divide both sides by 1.0 molar so that I can solve for this variable right here. We get a volume of 25 milliliters of the 1.0 molar solution is what would be required in order to make this dilution. So this is the explanation for this problem. This is a dilution problem in disguise. If you understand the process described by the words of the exercise, you will see in this picture in your head and realize this is a dilution problem. Notice that after water is added to the container, the concentration decreases from 1 molar to 0.1 molar. So if we have this original amount of 1 molar copper sulfate and then we dilute it with water to 250 milliliters, it becomes 0.1 molar. So what could that original volume have been? And we already solved the problem. This is 25 milliliters worth in order to have this concentration, and then when we added 225 more milliliters worth of water, it diluted it to a 0.1 molar concentration. Here's your note card for this section. Here are your 3 equations for molarity, and then the dilution equation, M1 times V1 equals M2 times V2. Anytime you have a volume change, or you've been given 2 different molarities of the same thing, then you're going to be using the dilution equation, or you have to consider it is a dilution. If you have a solute and it dissolves and you're given the molarity of the solute, then keep in mind that it's going to dissolve and separate, and you're going to use the stoichiometric coefficients in order to determine the molarity of the individual ions that were produced. So you can just use a mole-to-mole ratio from your given to the ion that you're trying to figure out to get the molarity of ions. And then always consider what's in the beaker. You will constantly be asked to draw molecular representations of problems that you're solving.